So hello everyone. I'm glad to talk to you, give you a short introduction today about machine learning from the perspective of mathematics and computer science. So you will see from my introduction how you can design a classifier to make a decision. That means if you have an image, then you want to see if there's a face or not in the image. You could use this kind of classifier to decide, and it works very well today in real time. And so you will see how actually what's the principle, what kind of mathematical problems you could ask in this domain, and up to what kind of practical. I will not be able to discuss the practical part of this kind of system, which is very complicated. But you will have an idea about the invention. That means the thing that behind these either mathematical inventions or computer science algorithm part that drives the practical applications behind these things. So I will go into quite a lot of mathematics today. So give you. Can you read the manual? Okay. Okay. So let me. Just to formalize a problem. So find So we want to find a function h between two space x and y. So x here, let me just denote a variable x. So this function, you take, for example, image, then it will tell you what category this image belongs to, and such that the probability that you are going to make a wrong decision, that means hx is not equals to some like what we call label or something, that y is the information that you have about x. Okay, that's the true decision. And this is your prediction. Hx is a prediction. And you are trying to count the chance that you are going to make a wrong decision, and when x, y follows some probability distribution d here. So this is a setup. And this space is so big, the space of H is so big that means when you open a book of machine learning, you see different ways to construct H. And so different chapters can be about one particular H. And nowadays a lot of people use deep learning, for example. This is I will discuss briefly at the end of the talk how this kind of function. So let me just be a bit brief. So x is the input, and y, what we call a label. So I'm here today just talk about two decisions, but you can generalize it to multiple decisions by changing the y into multiple options, choices here. And d is here the joint probability distribution. On the space x, y, and you could think about that the product space. And so what we want to do. So what is interesting here? What is the objective? So there is a concept called risk minimization. You could think of that as error minimization. So that is, you define an error. That's what I just mentioned. In terms of probability. And this error, we could write it as an expectation. By using an indicator function. That means if hx is not equal to y, then it equals 1, otherwise it equals to 0. And by taking this expectation, you got the probability. And then rewrite it as an integral. But the reason I do this, you will see that because I want to figure out what's the optimal edge here in this problem. That means if you can find this, then you solve the machine learning problem, and the topic is closed, and if it works. But the problem is that it's not so easy, as you will see. But at least we know what is the optimal solution. So objective is the risk minimization, and this minimal edge, what we call the edge bias. So you have a very particular edge bias. I will define that right now. You compute a conditional probability of y given x. So this conditional probability comes from the fact that xy follows the probability distribution. Then you have the joint distribution, then you can compute the conditional. And this conditional distribution, when you have that, you give me x, it will predict y equals 1 or minus 1. And then you take the argmax of this probability. And this makes sense if y equals 1 is larger, has a larger probability, then you will make that decision. Okay, so this is the edge bias. And the claim is that if you have a space let's say in probability measurable functions, and this edge bias is in this space, so normally it should be. This is a conditional probability. It should be nice, and then the risk that we talk about is optimal. It is probably not the unique solution, but at least you cannot do better than edge bias in the sense that the risk is not going to be smaller. And so this gives you like an ideal situation that if you know what is this conditional probability, then you can get compute this edge bias, and then you solve the problem. Just feel free to ask questions if there's any. So now let me give you a proof of this. So the proof So I'm talking about probability distribution D over a space X here. Let me assume that X is for simplicity in some continuous space, and Y is a discrete variable. So I can rewrite it using the conditional probabilities. Here you could interpret that as a density. This is a density. And then where there's a part of Y. So the notation is not very standard in probability, but for the simplicity. So you have this Bayes rule to give you a relation between the conditional probability of X conditional on Y and the Y conditional on X. And then you can rewrite this RD of H that I wrote on the top as the sum of Y equals, because there are only two options here, +1 or -1. Then you can integrate first on the space of X. That means then you get you count the number of the X and the Y that you will make an error over all the choices of X. You integrate over this joint distribution over X, then over Y. So this is double integral here over two variables. And you can separate that, so we can exchange the sum and the integral using Frobenius theorem. Then you have this two parts. If you have some data from X, then you the chance that it equals Y equals 1 is like that, is P. Then you make an error. Okay, this is one part of the error you will have. Or X belongs to -1. What's the chance that it belongs to -1? Is this probability. And then you make an error on this. So you have the two parts of the error, and these two parts of the error can be separated, can be minimized actually by the H Bayes that I want to show you here. So for the point is that for each X, just to consider some X that has lives in the support of the distribution of X, you wouldn't have any trouble, because if Px is 0, then the integral doesn't count, and you don't care about those points of X. And so just focus on these points, then we can find an optimal H on these points X. And this such that, so we can just minimize this for each X actually, this inside the integral for each term. And this minimization over, it's like a calculus of variations. You minimize a function of at each position. So you minimize the H actually here when X is fixed. And this is larger than this minimum probability. So you have two probabilities. y equals 1 or y equals minus 1 given x, then you, this sum is not going to be larger than the minimum, because 1 will be 0. Either one, the other one or the other will be 0. So either this term or that term will be in the sum, but they will not be larger than the minimum of each of the term. So that's and that's the smaller or equal. That means actually we have a lower bound of the risk, and this equality can be attained when h equals h base. Let me just argue that. So you have the equality when you have this. This is essentially, by the definition, it's probably a bit long. Let me just show you one case. So when you have h base x equals 1, then this thing, let me call it star. So h equals h base, and it equals to 1. Then it is not equal to minus 1. So you have this error which will count. That's the chance that x and y will become minus 1 when you observe x. And this is the this error is the minimum. So it is the minimum because this is the definition of h base, because you will take a conditional probability which is larger. So when you make a decision it equals 1, that means this probability is larger than the other one. And in this situation, these two are equal. And similarly, for h base equals minus 1, you will also attain the equality here. That means this is my conclusion. That means for any x, you have this equality when h equals h base, and among all those x which are on the support of the px, and you have the optimality. And then outside this support, they don't contribute to the risk, to the interval here. So that's why you have the conclusion that for any x, this works. Is that clear for you? So this is an ideal situation that you can, if you know the joint probability, then you know what's the optimal solution, and then everything is fine. In simple cases, for example, you have a. Let me just give you a simple example. These are examples actually quite standard in statistics. Let me just go. So or just to give you an example called mixture of Gaussian. So you have for example, two Gaussian distributions, then you mix them, and you observe something which comes from either one or the other. And this this you could specify something like that. You could say the probability that y equals 1 or minus 1, there's pi 0, or 1 minus pi 0. So we can just fix these numbers. This is the chance that you have a, what's the chance that you take an image, then you take a random patch of the image? What's the chance that it's going to be a face? Probably 0. Probably 0. It's almost impossible to find in a natural image some object. So pi 0 is almost very small in practice. And p of x conditioned on y well gives you some idea about x, what the distribution of x centered around mu1 and with some variance sigma 1. So this will gives you some idea about this this category. It will summarize actually the data from this category, and then from another category, you can have defined a different distribution from mu2. And the difficulty is that when mu1 is very close to mu2, compared relative to the variance, sigma 1, sigma 2, and then the separation is going to be more difficult. And the H-Bayes tells you what's the best you can do in this kind of situation when they are not very separable. Because if data are very easy to separate, and then you can have 100% accuracy, that means the risk is 0. But if your data has the distribution, they are very close to each other. And in this case, we can compute what is H-Bayes. So let me just write out the. This is possible to compute. Just compute this part. In case that the p conditional probability y equals 1 and y equals minus 1, they are the same, then it's very rare, but it's possible. Then you could make a random decision. But what's interesting is this is the boundary, and what's interesting is these two situations, and here you could verify that H-Bayes it equals 1 if so by writing out the Gaussian densities explicitly and use the Bayes rule, you get you get some comparison between, it's like a Euclidean distance but squared, and you compute and then normalize by the variance. And if x is close to mu2 compared to to mu1, if below some threshold, and this threshold this constant c depends on two things. It depends on the variance, the ratio of sigma 1 and the sigma 2, and the your prior pi 1 and pi 0. And so in this under this threshold, if this is very small compared to this, then you make a decision that X belongs to the first category, and the one category 1, that means you come from the mu2 sigma 2 distribution. So this is actually quite intuitive to think about this HBAS in this situation. And then based on this, there are many interesting classifiers. They were designed when data follow Gaussian distributions in high dimensions. And this is one. When you open a book, you will see this kind of classifiers. But it's not the full story of machine learning, because in practice, what really works is not from this theory, because we don't know what's the probability distribution from data like images. We don't know what is the probability distribution of a face. Even today, there are many interesting generative models can generate a very realistic image, but still we don't know what's the probability actually analytically from mathematical point of view. But computers now can generate this kind of images, which are very astonishing already. Yet, so let me go into another direction, which is to define classifier which doesn't depend on your probability distribution. So it's in some sense universal, independent of your probability D here. It works for no matter what kind of D. And so this direction opens a story called statistical machine learning. And there you will see a completely different story about machine learning. But at the end of the day, everything we talk about is about the risk minimization. So even you think about two different assumptions about different kind of theory of these assumptions, you have always the same objective, which is to minimize the risk. So let me give you an example more constructive. So it is called linear classifier. So what that means is that you have your data point on X. So I have, for example, a bunch of observations. Let's assume that we have X1. So let's assume there are m data points, and you know a prior that what time label it is, +1 label, and this is -1 label. And there we are trying to find a linear plane which can separate these two groups of points. And so this plane H is something like this. So it's a sine function which depends on two parameters, W and B, where W. So you make a decision by simply trying to figure out what is W and B. Once you have that, you have this linear line, and this line is where Wx is 0. So you have this. This is the decision boundary. And this is a linear plane. Now, and the setup is you have a collection of what we call training samples, and these training samples I would denote by S x1 y1 to xm ym on the space of x product of y, make m copies of that. And this, if you give me S, find H which depend on this data set, training data, in the space of H that we have just talked about. You find something which depends on your data. We don't no longer assume any probability distribution about the data. We just have some examples, and then we try to find a classifier in some space of H. So this depends on H such that let me make a few more stronger assumptions here. IID drawn from distribution D. Why we want this? Because if you want to evaluate your classifier on a set of examples X and Y, you will need to assume that where they come from. And typical assumption is that they come from the same distribution. So you're training, and so this is more about test. Okay, so you will compute this function by drawing samples from the same distribution, but they are independent of the training data samples. And in this setup, you can develop many interesting tools to argue that on what situation that you can control this error relative to what. So these kind of questions, then that's at the heart of the statistical learning theory. And now I'm not going to talk about that today. So I'm just going to give you a simple algorithm, which is called perceptron. Very early days. So it works like this. So for the moment, let me define H0, which doesn't consider the bias term. So that means B equals to 0. We will just have everything centered around the 0, and to separate these points. And this is a case that if you understand, then you can generalize that to the case with B is non-zero. So this algorithm works this way. So you repeat. So we initialize a counter k equals 0, then W0 is initial guess about this decision boundary, and so it's an initial guess of the classifier. Then we are going to do a loop to look at all the training data from 1 to m. There are m training data points. So if the prediction yk, k is at iteration k here, what's the value of w? Wk transpose xi, the sign it matches the true label yi. Then doing the same. Else, that means if we make an error, then we need to then we should correct our w depending on the sign of y. So if yi equals 1, then wk plus 1 then wk plus 1 equals wk plus xi. So we'll just add this pattern, what we call pattern xi, this data sample, into the weight. So it's like if this is a phase, then we'll add this phase to the weight. So at the end, if the algorithm works, this w will look like some averaged phase. in some situations, you can really interpret your classifier in this way. So else, you just subtract xi, and then you can loop. So the thing is,